All right. Good day, everyone. So welcome to FIT3143 lecture for week 10 of the semester. And in this week's lecture, we will go into SIMD, single instruction multiple data. So in the previous lecture, we were discussing about vector architectures. And prior to that, we will look into instruction level parallelism. So in this week's lecture, we will look into SIMD, single instruction multiple data, but we are not going to look into old architectures of SIMD, which is, back in the early 90s, we had the iliac SIMD architectures. We are going to go, we're not going to discuss that in today's lecture. Instead, I'm going to go more into how streaming-based SIMD, or better known as SFE, streaming SIMD extensions, were used by Intel and also eventually by AMD to provide advanced or accelerated data parallelism on the chip itself. Okay, and then so today's lecture is to give you an evolution of SIMD for microprocessors, especially in the SSE side, from the first version of SSE to SSE version 2, version 3, version 4, and AVX. So then later on, I will conclude to see how actually you can apply them in today's environment. If you have an Intel Core i7 processor, or if you have an AMD Ryzen or one of the newer generation AMD processors, how you can actually use streaming SIMD to actually help improve your data parallelism, especially if you're doing scientific computations, okay, using C or C++. All right. So as an announcement, this lecture is being recorded. A copy of the lecture will be made available to all of us after the class. So if you're not comfortable, you can always turn off your webcam and also mute your microphones, and you can ask your questions in the Zoom group chat. I'll try to answer them as much as possible. Nevertheless, I always encourage you all to use the microphones to ask some questions verbally if you have any doubts or you require any additional clarification. Okay, so let's go to the lecture screen. I want to share my screen. Before I share my screen, let me just make sure everything is in order. Okay, so everything is in order. All right, so I've shared my screen. So can you all see the screen? Just a simple yes or no will be fine. Okay, y'all can see the screen. Before that, wait, let me stop sharing first. I want to turn off my webcam so I can save bandwidth. Okay, thank you. All right, I'm going to share my screen again now. All right, sorry about that. Okay, so I'm sharing my screen again, so at least y'all can see hopefully y'all can see the shared screen. Okay, good. Okay, excellent. All right, so in today's lecture, so I'm going to, as usual, I like to annotate directly on top of it. So draw, probably use the red pen, and then after that I will auto hide the ribbon. Okay, so you get a better screen. Okay, so we'll go into single instruction multiple data with a focus towards streaming-based single instruction multiple data. So when this lecture notes here is very much theoretical. At the end of the lecture, I will bring you to an online website, an online tutorial that actually gives you a walkover on how you can use streaming SIMD extensions in C. Okay, that particular content will not appear in the exam. That's why I didn't put the content inside here, so that at least you know what is going to appear in the exam and what is something that you can learn at your own time. Okay. So the overview of today's lecture is that we will quickly recap Flynn's taxonomy, and then we will go into definition of SIMD, and then from there we will go into the streaming-based SIMD extensions, SSE. We will do a very brief comparison between SSE and MMX, and then we will cover the features of SSE, SSE version 2, version 3, version 4, and AVX. And then at the end of the lecture, I will just give you a very simple hands-on experience, hands-on exposure to AVX. Okay. And then after this, I hope all of you all will quickly go and see your processor architecture. What is the processor model, and then you'll go and see whether or not it supports AVX or not, which most likely it does. All right. So this falls within two parts: learning outcomes. Okay, the fundamental principles of parallel computing architectures. Design and develop. I'll give you some simple examples later on. Okay, so that is the idea for today's lecture. Okay, so in 1996, and sorry, in 1966, all right, just a minute. Okay, Michael Flynn came up with a taxonomy of different types of parallel computing architectures. So you have to understand, parallel computing was something that was looked into way back in the 60s and the 50s already. All right, so it's not something new. Parallel computing research, design, and development has been there for decades. All right, but Michael Flynn came up with an architecture that defines four main cores. So you have, this is what we call as SISD, single instruction, single data. So this is as much as your scalar processor goes. All right, and this was what all the earlier microprocessors are based on this. So if you go to the Intel, the earliest Intel processors, 8086. All right, then after that you go to the 8086, then the Intel 286 processors, 386, 486, and then the Pentium processors and so forth. Most of them were all based on single instruction, single data, scalar processors. And then after that, you have single instruction, multiple data. So single instruction, multiple data, back then they used to have dedicated architectures for this. So that's where we used to have the ELIAC, if I got my name, the name I pronounce it correctly, the ELIAC architectures. And then GPUs, okay, if you're doing GPU programming, they are using SIMDs, all right, or Intel SIMD. So this is where we'll discuss it on a bit. Okay, we'll go into this Intel SIMD extensions. So where you got one instructions, a single instruction, but this single instruction can be executed on multiple data by multiple processing units. So in a way, if you look at it, doesn't this look very similar to a vector processing? Indeed, it does. It has similarities to vector processing, which we have learned last year. Sorry, last year, my bad. Last week. Okay, just that in last week's vector processor, if you recall back, in a vector processor, you have multiple read, but the actual computation can be done serially. Is done serially depending on the on your vector architecture itself. Here, you have your processor has multiple processing units. Okay, all right. So there's multiple processing unit that allows you to do it in parallel. Okay, nice one there, Nicholas. All right, then, and then after that, you have multiple instructions, single data, MISD, sorry, this one we won't cover much. And then we got multiple instruction, multiple data. This is something that we'll cover a bit in today's lecture, and then we will cover more in next week's lecture. So next week's lecture, we are already going to conclude already. So after MIMD will appear as the last theoretical question in the exam. Then week 12, we will do a very brief overview of GPUs, and then we'll go a revision class already. So if you look at it, it's how much you have to learn and understand for the exams. It's I hope is manageable for everyone. Okay. All right. So what is single instruction multiple data? SIMD. So single instruction multiple data, also known as vector instructions, is a technique employed to achieve data level parallelism. Advantages is multiple data can be loaded at once. Operations can be applied to all of the data in one operation. So that's the whole idea. So as the diagram applies over here, you can have one instruction. Let's say I want to do a add instruction. Okay, this is an add instruction. And I want to do the add instruction for multiple data points simultaneously. So whether they're having to do a for loop, okay, I can just call one instruction, and this one instruction will load all 4 data points into memory. And you got 4 processing units, 3 or 4 processing units that actually can perform the add simultaneously. Okay, so it's like a vector. So as I mentioned, a vector is like a one-dimensional array. So think of it that way. You're doing a one-dimensional array addition, arithmetic operation, but you're not doing a for loop. You're doing it in one go. One go, you can execute all elements of the vector with the arithmetic operation. That is what SIMD means in essence. Okay. Now, of course, not all operations can be done in SIMD. SIMD is mostly for arithmetic operations. Okay, of course, you can do some other operations, but it's mostly tailored for arithmetic operations, whether you're doing addition, multiplication, division, subtraction operations. Okay, implementations require human labor in terms of coding. Yes, you need to do a bit of programming to actually call the right functions so that the compilers knows how to compile them. Okay, programming with particular SIMD instructions can involve low-level challenges, but this is mostly been addressed for you by the compiler and by the architecture these days. All right. So from here, we go into Intel SIMD extensions. So I'm going to talk about today what you can do with SIMD. All right. So Intel in the 90s, in the late 90s, okay, in the late 90s, okay, Intel actually first, if you look at the evolution of Intel, so maybe I can jump about 2 slides, or maybe okay, I'll jump here first. Now, in the mid 90s, okay, in the mid 90s, Intel introduced the MMX technology. So let's go to this slide over here. All right. So this is the the progression of Intel architectures. Now, prior to 1996, before this, you had what? You had Pentium 1. Okay, you guys were just the time you guys were not born yet. Okay, so I was a small kid back then. All right, and no, I was back then. You know, in the mid 90s, they used to do a lot of television advertisements about Pentium processors and things like that. And you know, I was a young kid wondering what the heck is MMX. They were saying Pentium MMX makes the processor perform very fast and things like that. So I was like looking at television and thinking, what is MMX? All right. Only when I learned in university what is MMX, I was like, okay, now it makes sense. Okay. So initially for scalar-based processors, for scalar-based processors in the early 90s, you have Pentium 1, Pentium 2. Okay. Then eventually they introduced Pentium MMX in 1997. Okay. So Pentium MMX, the MMX here stands for multimedia. I mean, Intel never really gave a formal term for the abbreviation MMX, but generally the industry considers it as multimedia extensions. Multimedia extensions. So what is the meaning of all of this? Okay, so let me bring you to a chip architecture. So this is not in the slides. I didn't want to put in the slides because I don't want to go too much into the hardware architecture, but just for the purpose of education, this is not gonna appear in an exam. Okay, so don't worry about it. Okay, this is I mean, a kind of like a microscopic picture taken of the Pentium 4. So Pentium 4 came out in the early 2000. All right. So this shows the entire circuit architecture from, I mean, they haven't gone deep into it, but this is like a microscopic layer at maybe a certain zoom level, okay, into the architecture. And what we can see over here, okay, you can see that these are all the different electronics components, the circuits that actually make up the entire Pentium 4 architecture. So here you can see at this point, you have your instruction fetch and the branch prediction. We discussed this in ILP in week 8's lecture, how Intel were able to achieve out of order execution. So the circuitry, the hardware execution is all done over here. All right, instruction decode. All right, instruction tree cache, the execution pipelining. All right, and then you have the integer execution core over here. All right, now the thing I want to show you all is actually here, where is it? Here, over here, the registers. So all the registers are stored here. Okay, the registers are stored over here. So the registers are actually hardware variables that stores instruction variable content. All right. So here you got floating point registers, and then here you got your MMX and your SSC registers. So you got MMX. So here you got the MMX arithmetic logical unit. So what is MMX? So in 1997, Intel introduced additional enhancements to their Pentium architecture. So which means if you look at here, they actually introduce an additional circuit to their Pentium architectures that allows them to perform vector operation. Vector operation. So vector operation means that, let's say, if I have two vectors, vector A, vector B, two integer vectors, vector A and vector B. All right, say vector A. So vectors are one-dimensional arrays. So vector A contains, let's say, vector A contains. So maybe I'll just put it as like this. Okay. So let's say vector A contains four each. Okay, four 16-bit integers. Okay, 16-bit integer values. Okay, and then the same thing here for vector B. Okay, so now if I were to ask you, I want you to sum each element here. I want you to sum each element of the vector inside here. If you were to write a C code, what would you do? You would do what? For I equals to 0, I is less than the size of the vector. Let's say this case is 4. And then after that, you do what? I plus plus. And then what do? You do C of I is equals to what? A of I plus B of I. This is what you would do if you had a scalar processor. Okay, you know this, I know this, we all know this already by now. Okay, now how cool would it be if rather than having to do this, I can just call C equals to A plus B, whereby I would have some form of a vector processor that can perform the summation of all elements of the vector simultaneously in one go. And that is what Intel achieved by introducing the MMX architecture back in the mid to late 90s. All right. So in that architecture over here, they actually included some additional circuitry, arithmetic logical units that actually allows you to perform vector computation, vector arithmetic operations. But these vector arithmetic operations were using, they had their own registers. Sorry. They had their own registers. These registers were residing somewhere around here. These registers are based on 64-bit registers. That's why I put here 16, 16, 16, 16. Each register, this is actually one register. Okay, each register can store 64 bits. Okay, it can store 64 bits of integer values. Okay, so they got a set of, they actually provided 8 registers. They actually provided 8 registers, and each register stores a 16-bit integer value. And then once you load these registers, once you load the values into these registers, and then you can call the vector code that will actually perform the summation simultaneously using the MMX architecture circuit over here. That is what Intel introduced in the mid to late 90s to actually help improve data parallelism. That is the MMX architecture. So you can see over here, if I go one slide up now, we actually had 64-bit MMX registers. The MMX registers were named from MM0 to MM7. So each register is 64-bit. Each register can pack. You can pack integers into them. So as I mentioned here, you can pack four 16-bit registers. 16-bit, I just put 16B over here for bits. You can pack 4 16-bit registers into one MMX register. You can do the same for another MMX register, and then you can do the arithmetic operations simultaneously without having to do any for loop. Okay. Now, the problem with the MMX registers, although as revolutionary it might sound, I mean, revolution is a strong word, as impactful as it may sound in the mid-90s to introduce MMX, the problem with MMX was Intel was sharing the MMX registers with the floating point registers. So Intel also had a floating point adder. So remember, you have an integer component to do integer operations. But to do floating point operations, you need to have an extra circuitry here. So don't worry about this. This is not going to appear in the exam. It's just for knowledge for you all. So at least you all can relate a bit more better. So they used to have a floating point architecture inside here to perform floating point operations. Floating point means real numbers. So if we have real values like 3.5, you want to add it with 5.5. So when you store them into a float variable, the compiler then will generate the binary, which will then execute these operations using a floating point circuit of the microprocessor. But the problem was the MMX registers were using the floating point registers actually. So when you are doing floating point operations, you cannot do MMX operations. When you're doing MMX operations, you cannot do floating point operations. So that was one of the limitations. That was one of the limitations of the MMX architecture back in the late 90s. Okay, in the mid to late 90s. All right. Then in 1999, before the new millennium, Intel decided, screw it. I'm not going to have the problem where I need to share the MMX registers with the floating point registers. I came up with a brand new architecture, a brand new instruction set called SSE. SSE stands for streaming SIMD extensions. Okay, streaming SIMD extensions, SSE. All right, so then from there, they evolved SSE to SSE2 in the new millennium. Then after that, SSE3, SSE4, SSE 4.2, and then in 2011, they introduced AVX, AVX2, and then today we have AVX 512. So this is the history of how SIMD has evolved. And all of this you can use today. With the right code, you can actually program AVX instructions today. I will give you a brief hands-on lecture, hands-on activity at the end of the lecture before we conclude. So at least then you know, I can do this today. So that is why this is actually a very interesting lecture. All right. Okay. So that is how started from MMX, and then we progress to SSE over here. All right. So that is how the progression work. So you can see the progression from 1995 to 2010. So this is quite an old diagram, but anyway, it still has relevance. Okay, so you can see in the mid 90s. Okay, now by mind, I'm not showing this being an Intel advocate or anything like that. I'm just showing this because it's easier to get information about architectures for education from Intel. AMD, I'm finding it a bit hard to get information. Maybe I'm not searching hard enough. All right. But today we can see that AMD has made a lot of inroads, and they are now doing way better than, at some point, better than Intel in multi-core and even single-core architectures. But anyway, for the purpose of education, we are looking at the x86 architecture progression based on Intel architectures. All right. So if you look into here, all right, if you look at SIMD, how SIMD has progressed, started with MMX, and then from there, when you had SSE, you can see that SIMD play a very important role in being able to execute, okay, how many millions per instructions per second. All right. So you can see over here, it actually had a very big impact. How SIMD, the streaming SIMD actually made a very big impact on improving the performance of your parallel architecture. And then when you had task level parallelism came when you had your multi-core architecture. So the green area is what we have done earlier in the semester. The green zone is what we have done in the beginning part of the semester, where we did threads. Remember, we used POSIX threads to actually achieve data parallelism using multi-core architectures. All right. Now we are going a bit back into the past, or in the current today, in fact, where we are using the SIMD. How can we leverage on SIMD to actually improve our data parallelism? Okay, so this is how MMX was based on. MMX was based on using, they defined 8 registers, 8 64-bit registers to pack. So you can pack 32-bit variables or 16-bit variables into here. 16-bit integers, 16 bits integers into here. Sorry, there's no S. Okay, 16-bit integers into the registers. And once you pack them, then you can call a vector operation. You can call a vector operation to actually do an add operation. You call a vector add operation. I just call it vector add. And then you pass in the registers inside here. MM0, MM1, and then it will perform a simultaneous add using the MMX arithmetic logical unit on board the processor itself. But the problem was the MMX registers were sharing. They were sharing the floating point registers. The floating point registers were based on 87-bit registers. They were sharing the registers inside here. So what Intel did was, when they came up with the streaming SIMD extensions, SSE, all right, they came out with eight new 128-bit registers known as XMM0. So they added the abbreviation X inside here. So to separate them, MMX in 1997, MMX, they came out with new registers, MM0 all the way to MM7. And these were sharing the floating point registers in 1997. In 1999, Intel introduced SSE, and in SSE, they came out with the XMM0 registers all the way to XMM7 registers. So these are brand new registers. These are not sharing, these are brand new registers, and these are all floating point registers. 32-bit, these are all 128-bit floating point registers. So they can perform 120-bit registers for floating point operations. Okay, for floating point operations over here. All right, so then eventually when they started introducing the 64-bit architectures, then they extended it to 16 registers for SSE. Okay, 16 registers. So the SSE adds the following features to the 32-bit architecture. Okay, so each 828-bit XMM registers, and then 16 XMM registers in 64-bit mode. Okay, then you got 32-bit MX PSI registers. We perform control and status bit. So this is not important. All right, so this is just for knowledge. 128-bit packed single precision floating point data type. Okay, and instructions that perform a SIMD operation on single precision floating point values that extend the SIMD operations that can be performed on integers. So if you're using these registers over here, either the additional 8 registers or the original 828-bit registers, you can perform arithmetic operations. Okay, you can perform 128-bit packed and scalar single precision floating point instructions. Whereas if you're doing integer operations, you still use back the MMX registers. So which means that if you're doing floating point, arithmetic operations, and you want to leverage on the SIMD parallelism, you use SSE over here. Okay, you use SSE over here. If you're still doing integer-based operations, then you still use back the MMX registers. This is for SSE1. All right, SSE1. All right, and then so the ability to perform SIMD operations on 4 packed single precision floating point values enhances the performance of the 32-bit processors for advanced multimedia applications. So if you're doing image processing, okay, if you're doing video processing, if you're doing audio processing, which requires a lot of parallelism, vector parallelism, this is where you can actually benefit by using the MMX and also the SSE instruction set. All right. So the cache control instructions is to help stream data in and out. It's not important. It's just for your own knowledge over here. All right. So so this is some of the information over here. So I'll go to this. So you can see over here. All right. The SSE programming environment, they introduced the XMM registers. Okay, so this is the X stands for extended multimedia registers, where each 828-bit registers used to operate on either packed or scalar single precision floating point data. This is for the control registers. So this is not something that we will look in detail. So the one that we want to look here is this one. This is the ones that are important for us to know. So over here, you have 8 of these registers. So you can see XMM0 all the way over here. So which means, technically speaking, I can actually now pack 32 bits of floating point values, floating point numbers. Same thing over here, 32 bits of floating point numbers over here. And then I can perform a vector operation of these 32-bit floating point values simultaneously. So hence the term single instruction, multiple data. The multiple data here refers to the fact that you have 4 different data in a vector. 4 different data in a vector for two registers. Okay. And then the single instruction here refers to that you're performing an arithmetic operation, let's say add, of all of these elements in the vector simultaneously. That's the term of single instruction, multiple data. All right. So as the 128-bit XMM registers are additional program states that the operating system must preserve, they are disabled by default until the operating system enables them. So this is normally enabled by the operating system. All right. Now, what is the advantages of SSE over MMX? So we have to go back to the history again. Look back at this slide again. Okay, what is the advantages? How is SSE better than MMX? So let's go back to here again. Okay. So SSE creates 8 brand new registers. So if you look at the diagram again here, this is a Pentium 4. Pentium 4 already had SSE. So you can see over here, they already created over here, all right, 8 brand new registers for SSE inside here. All right, brand new registers, which is not sharing with the floating point instruction, floating point registers. All right. Now, bear in mind, SSE supports floating point data. It primarily supports floating point data. SSE to support integers will need to use MMX. Whereas if you're using MMX only works on integers. So again, to compare again, okay, MMX, SSE. Okay, MMX does what? MMX has 8 64-bit registers. Okay, only perform integer operation. SSE introduces 8 new 128-bit registers. Okay, the registers here name are MM0 to MM7. Here you have XMM0 to XMM7, and you can go all the way to XMM15 if you're using the 64-bit architecture. And these are used for floating point operations. If you want to do integer, for integer base, you go back to, you will use the MMX part of the SSE architecture. All right. So which means in an SSE architecture, you still have MMX inside there. It's just that MMX within SSE is used for integer operations. Whereas if you're doing floating point operations, you will use the SSE registers over here. All right. So this is what they do. So in the SSE data type, you have 128-bit register. So with the register grows all the way to 128-bit. Bear in mind, it is not cheap to actually design a circuit which can store a 128-bit register. So this requires a lot of advancements in the chip architecture also. All right. Each of them can store a 32-bit floating point variable. How do you store a 32-bit floating point variable? You use the IEEE 32-bit single precision floating point values, which is then packed into a quad word format over here. Okay, and then once you can perform conversion operations. All right. So I got a question privately. Every new version of SSE is just adding new registers. Okay, so this is a good question. I thought maybe I should add in inside here. Maybe I'll open my notepad. All right. Okay, so does every new version of SSE adding a new register? No, not really. Okay, SSE2 adds new instructions as well. Okay, so they also add new instructions. So later on we will see what is the increments to that. All right. Okay, so so now the question comes, how do you store a real value? This is a real value. This is a real number. How do you store a real number into a 32-bit This is a 32-bit float variable. Now, many of you all take this for granted. I mean, this is not going to appear in the exam, so don't I mean, I mean, just want to just want to inform you out upfront, so at least you all don't get perturbed about it. But it's just something I thought would be nice for you all to know. So let's say you got a float variable. Let's say I declare a float variable, float A equals to 0.15625. Have you ever thought how is a real number stored into a register? Because at the end of the day, the register stores binary values. Okay, how do you do it? Okay, so if you actually use the IEEE 32-bit floating point convention format, you can find it online. Okay, what it does, okay, it does this. Okay, first you convert the 0.15625, you convert the 0.15625, you convert this to a binary value. So what is the binary of 0.15625? Who can tell me? How do you convert a real number to a binary value? Okay, decimal you all know already. I mean the round value you all know, but how about the fractional value? How do you do that? So what you do, okay, what you do is you first, maybe I'll just do it down here. Is there, maybe I need a bit of space. Maybe I can open my whiteboard a bit. Okay. This is for the previous video. Okay. So let's say you take 0.15625. Okay, this is a process. You multiply by 2. What do you get? You get 0.3125. So this 0 you add to the first binary 2 value. Then after that, you take what? You take 0.3125 multiply by 2. What do you get? 0.625. So this 0 you add to here also. So you get another 0 up here. And then 0.625 multiplied by 2, what do you get? You get 1.25. So this 1 you add up here. So you get 1 here. All right. I think you see where I'm going already. Yeah. And then after that, sorry, there's a 1.25 here. And then 1. Dang. Okay. And then 1.25 times 2 gave you what? 2. Sorry. Not 1.25. My bad. You don't want, you only want the fractional part. So 0.25 times 2 will give me what? 0.5. Again, you take the 0 and you put it here. Get 0. And then you take the fractional part again. 0.5 times 2 gives me what? 1.0. And then you put a 1 over here. And then the 0 is done. You can stop here already. So which means 0.15625 base 10 is equals to what? It's equals to 0. It's equals to 0.00101 base 2. That is how you convert first. So you convert this base 10 real value to a binary value. But then how do you store this binary value as a 32-bit single precision floating point number? Now, this is by the definition of the IEEE format. So I'm going to explain to you the process. Now, why is that so? I'll skip that part. I will let you all, you can actually, before online, you can just go to the IEEE single precision floating format. There's a website that explains to you how to do it. All right. But what you want to do is first, the first step you do is first you identify the sign. So this is a 0.15625. It's a positive number. It's not a negative number. So the sign bit will be 0. If it's a negative number, if it's let's say negative 4.5, then negative here, then the sign bit will be 1. All right. Okay. Then after that, what you get, you take this binary value, you move it. If you move to the left, it's plus. If you move to the right, it's a minus. So you move it how many points until you reach the first binary 1. So in this case, you move it by 3 points. So you move it by 3 points. So this becomes what? 1.01 times 2 to the power of minus 3. Okay, 1.01 times 2 to the power minus 3. You take the exponent minus 3, you plus with 127. This will give you 124. And then 124 base 10, you convert to binary, you will get 11111 base 0 11111 00 00 base 2. This takes up the exponent bit. So you can see 1111100. This is actually the take the exponent plus 127. All right. Then the fraction will then take the remaining values here, which is what? 0, 1 here, and then you pad zeros at the back here. So that is how you can represent a real value into a 32-bit float variable, a floating point register, a 32-bit floating point register. So this is, this is something very useful. How useful it is to you is up to you all, but at least I hope it comes in handy for you all down the road. All right, this is not going to appear in an exam, so don't worry about it. It's just some added knowledge for you all to take away from this unit. All right. So if you have four variables, let's say float A, then you have float B. Let's say float B is equals to 4.5, and then you got float C. Let's say float C equals to 9.6, and then let's say I got float D. I got 4 float variables. Float D is equals to 9.9. All right. What happens is each of these float variables will be converted into this format, and then they will be packed into these four registers of a SST register, XMM0, for example. So let's say this is XMM0. So the float variable A, which contains 0.15625, will be converted into the 32-bit register over here. And this 32-bit register value will be packed into here. So you'll get your 0, and then what you got inside here, your 0, 1, 2, 3, 4, 5. So inside here, you got your 0, 1, 2, 3, 4, 5, and then 0, 0. And then after that, what do you have inside here? You have your 0, 1, and then all the zeros here. So this is your 0.156, 15625. And then the same thing, your 4.5 will be packed into here, and so forth. Your 9.6 and 9.9. The values is now I put in the following slide. So once you have packed them into here, and then you do the same thing for another registers, and then now you can call an arithmetic operation that will add the values simultaneously. Hence the term vector processing, and then the term SIMD. All right, that is how it actually works over here. Okay, all right. So now this is very important. Okay, when I say it's important, I hope you take note of this. All right, SST version 1 adds 70 new instructions. Okay, 70 new instructions. So this instruction, as I mentioned, the add, subtract instructions inside there. Okay, that have 4 functional groups. So the instructions can do 4 things. You have instructions to actually pack data into the registers. So you need instructions to actually move data into the registers. All right. Then you have instructions to perform integer operations. You have instructions for state management instructions and instructions for cache control, prefetch, and memory ordering instructions. All right. Okay. So the instructions for SSE, the first one, okay, the packed and scalar floating point instructions. You can do data movement instructions, arithmetic instructions, logical comparison, shuffle, and conversions. So these are all the instructions they provide you to do. So we haven't looked at the instructions yet. I haven't showed you the instructions yet. Okay, now I'm just explaining you the concept first. All right. So let's look at one example over here. Okay, let's look at one example over here. It's a bit small. Maybe okay. Here we have a scalar single precision floating point operation. So the scalar single precision floating point operation operates on the lowest lowest least significant double words of two source operands, x0 and y0. So scalar means you only perform at the lowest part here. So if you're wondering earlier, isn't it? What is scalar? What was talking about scalar and pact? Okay. Now we're looking at scalar. Scalar is over here. Scalar means you have a 128-bit register. This is a 128-bit SSE register. All right. Okay, so let's say this is XMM0. This is XMM1. You populate them with 4 different float values. Okay, you perform them four different float values for XMM0. You do the same thing for XMM1. You populate them with 4 different float values. And then after that, you call the operation, the operand. So if you are doing a scalar operation, the scalar operation will only take the least significant double word. Okay, the least significant double words of the two sources, in this case x0, y0, add them and put the answer here. The rest of the answer will contain from the first register. Okay. Now, if you're doing pact means it will do everything. X1 plus Y1, X2 plus Y2, X3 plus Y3. Okay. If it's scalar, is this one only. If it's pact, it will do all of them together. All right. So now let's go to SSE version 2. So when did SSE version 2 come out? So if you go back to the slide top here again, SSE version 2 was introduced in the year 2000. In the new millennium, they introduced SSE version 2. All right. So SSE version 2, okay, what SSE version 2 did was added new math instructions for double precision. So now not only you can perform single precision, you can perform double precision vector operations. So now you can use the double variable. Okay, double variable, and also extends the MMX instructions to perform on 128-bit XMMM register. So which means that SSE2 no longer relies, SSE2 now means that you can perform integer and floating point operations. You can perform integer and floating point operations on the XMM registers. Now, it's a big difference. In SSE version 1, you can only perform floating point operations on the XMM registers. Sorry, this is a very bad writing, registers. Okay. In SSE version 1, you can only perform floating point operations on the XMM registers. In SSE version 2, you can perform both integer and floating point operations on the XMM registers without the need to use the old MMX. So SSE2 onwards, they already move away from MMX. All right. So SSE2 provides additional data types, double precision, okay, byte, word, double word, and quad word. And then the instructions now, they allow you to do both pact and scalar, double precision floating point instructions. They also provide additional 64-bit and 128-bit integer instructions. All right. And they perform additional cacheability control also. So this is the, okay, so this is a bit lengthy, so don't get perturbed about it. Okay. So the new features here, so this is just some additional information. So this is not crucial. Okay, not crucial information. Not crucial, just for added knowledge. For added knowledge. So I just put this here as a point so that you know that this is not something that you need to remember. All right. So they provide the ability to perform SIMD operations, higher precisions, additional flexibilities. They provide the ability to operate 128-bit packed integers. Okay, programmers can develop an algorithms that finely mix single and double precisions, and also extend the support SSC for cache and controlling. Okay, so what it works is this. Now, this is where, oops, I think there's a mistake over here. I should have moved this higher. Sorry. Okay, so this is where SSE2 comes in. SSE2 works here very well. Now, SSE1, if you look at SSE1, SSE1, in SSE1 or just SSE alone, you had a 128-bit register. This is the XMM register. Okay, and the register you can pack a maximum of 4 32-bit 32-bit floating point variables, 4 of them. Okay, 4 of them you can pack. Float. Now, SSE version 2 says more flexible now. You can put double precision floating point variables. You can put 2 double variables here. You can pack byte integers. You can pack 16-bit, 2 byte integers, short integers, 2 byte integers. You can pack double word integers or even float. Or you can even pack quad word integers, which means long integers. So it gives you a greater degree of flexibility. So SSE2 was when Intel started, Intel and eventually AMD. AMD also had introduced their own their SSE also. Okay, so SSE was when microprocessors was able to leverage on the SIMD instruction set architecture. All right. So now you can perform packed operations. So packed operation means that all of the registers, all of the vector values within the registers are involved in the operation, whether you're doing an addition, a subtraction, and so forth. Okay, that is what it's doing over here. All right, the scalar still, you can still perform scalar operation, but you can also now perform packed operation. But remember, SSE2 performs vertical. It's a vertical operation. Vertical meaning that if you have, let's say, XMM0 here, you have XMM1 over here. So you take the first, let's say this is a double precision operation. Double precision operation. So you got 2 double variables here, 2 double variables here. It takes X0 and XY0, sum them, does the arithmetic operation and store the answer into the, let's say, XMM2 register. It does the same thing. It takes X1, add Y1, and stores it into the upper 32, the upper 64 bits of the XMM2 register. So remember, this is a 128-bit register. All right. Okay. And this is scalar operation over here. So very straightforward. So now you see we are going faster already. Yeah? So it's not, you look at it, it's not a lot actually. It's a pretty straightforward lecture. SSE3. So when was SSE3 introduced? Year 2001, I'm not mistaken. When Pentium 4. Okay, when Pentium 4 started, they started SSE3. They introduced 13 new instructions. SSE3 didn't introduce new data types. Okay, they used the previous version SSE3 SSE2 instructions, but the most notable change, so this is important, the most notable change here is to do horizontal operations within a register. And second thing, okay, also added instructions to perform different operations on a SIMD data. So you can do subtractions on the first pair of data and additions on the second pair of data. So which means SSE3, although SSE3 represents an incremental update to SSE2, okay, in the sense that SSE3 focuses more on introducing a few more instructions. But the most notable one, this is important, is that the fact that you can perform horizontal operations and you can perform different operations for different parts of the vectors in the register. So which means that here, we are actually going towards MIMD, multiple instruction, multiple data. All right. So these are the two main features of SSE version 3. The two main features of it. The first one is that in your 128-bit registers, okay, 128-bit registers, you can now perform horizontal add. So rather than going vertical, you can now take x1 and x0, sum them up and put inside here into your answer. You can take y1 and y0, sum them up and put the answers into the upper 364-bit of the registers. So they call it horizontal computation, or the name is called horizontal add, packed double precision. The PD here means packed double precision. Okay, these are the assembly functions. We're not going to use this. We're going to use our other function names when I go to the practical exercise later on. Okay, and then the second one is that you can perform asymmetric processing. So this is important. Please remember this. Asymmetric processing, where now you can perform add and subtraction, but this has to go vertical. Okay, in this example is vertical of the add and sub. So you can do add and sub, packed double precision. So this goes in vertical. So this is in a way promoting MIMD, because you got multiple instructions now. You got add and subtraction by working on multiple data. So I mean, well, yeah, in a way it's multiple data. I mean, in a way it's going to MIMD. All right. Okay. Now after that, they introduced supplemental SS3. So supplemental SS3 is a minor increment to SS3, where they provide some additional 32 instructions to accelerate the variety of multimedia and signal processing applications. Okay, so they can perform additional things, which includes the horizontal computational, packed horizontal add double. So you can perform, you can increase the scale of the horizontal computation. That's a body for SSE3. As supplementary SSE3. So very briefly, I'll go through this. Now, SSE4 started in, if you go back to the timeline again, SSE4 started when? Here. Okay, in the late 2008, when 2006, when Intel started their multi-core. This is when they started going to the multi-core realm. 2 cores, dual core, quad core, hexa-core, octa-core today. All right. So in the multi-core RAM, when they went to the multi-core RAM, they started introducing the SSE version 4 instruction set. So in SSE version 4 instruction set, if you look at SSE version 4, okay, so SSE version 4 was built on a 45 nanometer process technology. 45 nanometer is considered ancient today. 45 nanometer means that the size of the gate, the size of the transistor gate, is about 45 nanometers. Okay, so the smaller the gate transistors, the more transistors you can pack into a single processor and also making more power efficient. Today Intel is really working very hard to get 10 nanometers process technology working, whereas AMD is now going into 7 nanometers process technology already. So this is just the process technology over here. All right. So SSE4, they provide 2 versions, 4.1 and 4.2. All right. They add new instructions to improve compiler vectorizations. All right. And they improve performance in string and text processing. Okay, that's about it. SSE4 doesn't support operations on MMX anymore. So SSE4 has really totally gone beyond MMX already. MMX is legacy. And then after SSE4, we have what we're going to do today later on, advanced vector extensions, AVX. Okay, AVX, the main thing from AVX is it increases the registers, the XMM registers, from 128 bits to 256 bits. So now let's look into history here. Okay. So MMX, SSE, SSE1, SSE2, SSE3, SSE4, and then AVX. So 64-bit vector registers, 128-bit vector registers, and then AVX went to 256-bit vector registers, and eventually AVX version 2, AVX2, went all the way to 512-bit registers. So the larger the register, the more data you can pack into the register, which means you can perform a higher degree of data parallelism in every single operation. So that is what the AVX512 is trying to explain to you over here. So you can see this XMM0, XMM1, these are all based on SSE. SSE 1 to SSE 4 instruction, SIMD instructions. AVX is 128 bits, 256 bits, and then all the way here you got 512 bits registers. They call it as Z registers. So if you're doing assembly language, you will use this register name. But we're not going to use register names. Instead, we're going to use C programming to actually do it for us. All right. So you can see over here with SSE AVX, with the AVX 200, this is AVX1. You can actually, with AVX1, with 256 bits register, okay, you can pack how many? You can pack 1, 2, 3, 4, 5, 6, 7, 8. You can pack 8 floating point, 8 float variables. So if you have a vector, or an array of 8 elements, you can perform an addition simultaneously of 8 elements of a vector with another 8 elements of the vector in one single operation. Hence the term SIMD. All right. Okay. So that's about it. So that's what today's lecture is going to discuss about. So it's fairly straightforward. SSE, AVX, okay, and then to program, how you can program SSE in your code. So now you understand. Wow, I didn't know I can do SSE. So how do you know? Do you have SSE on the computer? How do you know? How do you know what version of SSE or AVX do you have? Anyone want to tell me? I'm going to skip the break today, because we can end soon already. Okay, so I'll skip the break today. So I'll just quickly we can end the class soon today. You don't have to go all the way until 2 o'clock. Okay, let's take a breather a bit. So how can you all tell that your processor supports AVX or what? How can you all tell? Anyone want to tell me? Give me an idea. Device manager, that's one way. Device manager. How do you do that, device manager? I'm quite keen to know. One way I know of is that okay, you go to your disk PC here, you right click on your disk PC here, you go to your properties. You can see, okay, like this is my laptop. It's running a Core i7 9750H. You can do that also. ISCPU, you can do that also in Ubuntu, yes. But if you want to know the details, okay, this is what normally I will do. Okay, I'm a bit old school then. If you go to Arkin, if you just type Intel Core i7 9750H, all right, and then you go inside here, you can actually see the full support provided inside here. So instruction set extension, they provide 4.1, 4.2, all the way to AVX for AVX2. So this is one way I normally do. So if you have an Intel processor, you can actually just go to Arc Intel, and then you can find out all the information about your instruction set support inside here. Okay. So to program SSE, you can do your assembly language, which we're not going to do here. Okay. Another semester to learn. All right. We can use C++ vector classes, C or C++ vector classes. We can use optimized function libraries, compilers, or we can use the intrinsic functions, which we will cover later on. Documentation for SSE can be provided here. I've given you a link inside here already. You can go and click on the link. You can click here, and then it will bring you to some websites here that explains to you the streaming SIMD instructions here. But this is all for you to refer to. Or can you look at the Intel intrinsic guides and things like that, or you can look at AMD. AMD also provides instructions for SSE. Okay, that is the reference for today's lecture. So to summarize, okay, to summarize, Flynn's taxonomy covered 4 architectures way back in '66. Single instruction, single data set, multi-instruction, single data set, single instruction, multiple data, SIMD, and multiple instruction, multiple data. So we will do more on MIMD next week, but today we discuss about SIMD. All right. Okay. Definition of SIMD is a Vector instructions, techniques as if data parallelism, where you can perform multiple data can be loaded at once, and you can perform an operation on all this data in one simultaneously. All right. And then from there, we went into streaming SIMD. So streaming SIMD are a set of instructions provided to improve the SIMD operations on a microprocessor. We discussed briefly about before SIMD, before SSC, we had MMX, and how SSC compares the MMX. And then we discussed SSC version 1, version 2, version 3, version 4, and we briefly covered AVX. That is today's lecture as a whole. So very straightforward, not difficult. Okay, the important ones is to actually understand the difference between MMX and SIMD, SSC, and to understand the basic features of SSC version 1, SSC version 2. Okay, SSC version, this is not important. This is just for you all to understand how you can convert a floating point number into a 32-bit floating point register. Okay, and then after that, you understand the difference between scalar and packed floating point instructions. And then you understand what's the difference between SSC version 2 and SSC version 1. All right, and then you go into SSC version 3, SSC version 3, and then we talked about SSC version 3 is the important thing. SSC version 3 is the two very important things: horizontal computation and asymmetric processing. And then SSC version 4, where it just performs some additional instructions, and then AVX, where AVX did 256-bit instructions registers. All right. So if I could add an extra slide over here. All right. So if I have to draw, so we had MMX. Okay, MMX had 64-bit integer registers, which shares the floating point unit registers, FPU registers. Okay, and then they provide vector instructions for these registers over here. So you can pack and do vector arithmetic instructions over here. All right. So you had MM0 to MM7 registers. This was in 1997. Okay. This is 1 year after the movie Independence Day came out. Greatest movie ever made. It's a bit of a joke. Okay. I mean, it's a nice movie. I really enjoy. Okay. Something just off topic a bit. Then after that in 1999 you had SSE. Okay, in 1999 you had SSE coming out. SSE introduced a 128-bit registers, separate registers, no longer shares with FPUs. These are all for floating point operations. Floating point operations. Okay, so you had XMM0 all the way to XMM7 and all the way to XMM15 if you're doing the 64-bit architecture. For integer-based operations, for integer-based operations, you still, for integer-based vector operations, you still refer back to your MMS architecture. And then after that, in the year 2000, in the new millennium, they introduced SSC version 2. So SSC version 2 extended the 128-bit registers to now allow you to perform both floating point and integer operations. So you no longer need to rely on the MMX anymore already. Okay, still you have your XMM0 to XMM15 registers, 128-bit registers. Okay, and then they provide the instructions also. In 2001, okay, in 2001, what they did? Oops, sorry. Okay, in 2001, they introduced SSE 3. If I'm not mistaken, is it 2001? Let me check and see the timeline again. It will be correct. SSE 3 came on in 2000. Oh, my bad. No. 2004. My bad. SSE came on in 2004. SSE 4 came on in 2007. Okay. Okay. All right. So go back here again. Sorry, this is a typo. 2003. Yeah. SSE 3 came out. Also 128-bit registers. Okay, but most importantly, they allowed for horizontal operations, and also asymmetric operations. And then you got supplementary SS3. I'll skip that. And then in 2004, 2007, sorry, you had SSE 4, which added more new instructions, for better vector operations. And then finally, in the year, what year was it again? In the year 2011. Okay, 2011. In the year 2011, I'm eating up a bit of slide. In the year 2011, you had your AVX, where you introduced the 256-bit register. And then after that, if I go down a bit here, AVX2 came up with a 512-bit register. Okay, this is the YMM registers, and then this is the ZMM registers. This one came on in the year 2013. So you saw the progression of SIMD. This is the progression of SIMD on consumer microprocessors, consumer and also for enterprise-based microprocessors to help you improve your data parallelism. Is that clear, guys and girls? Is that okay? All right, good, Nasser. Thank you for feedback. Okay. All right, so that's it. Okay, okay, thank you. So that's it for the lecture. All right, so now I'm going to go back to Moodle. So in Moodle, in this week's lecture, we have added in, we're putting a pre-class activity, but I just put it inside here. Okay, so I've added a link here. Crunching numbers with AVX and AVX2 by Matt Scarpino. Okay, so this is an online article which provides an explanation on performing mathematical SIMD processing in C using Intel's advanced vector extensions, intrinsic functions with code examples. The code of this online article will not, the content of this online article will not appear in your exam. So the coding exercise here is not going to appear in the exam. Yes, the topic in the lecture, some parts will appear in the exam, but the coding inside here will not appear in the exam. So you refer to this as an additional hands-on resource to improve your comprehension on data parallelism. This online article aims to provide some good practical exposure on how you can use AVX to increase the data parallelism of your program. So let's go to the article here. Okay. All right. So this article, you all can go through. This is an easy article. Okay, you all can go through. You can download all the examples over here. It's in the download. I think you need to register a Code Project account and download it, but it's free. All right. So Code Project in today might not be very popular to you all, but during my time was like the go-to place for code resources. I mean, now Stack Overflow is every programmer's best friend already. Okay. So anyway, so what we are doing, this site provides how you can actually do SSE or AVX programming in C, vector programming. All right. So they are using AVX here. They're not using SSE because AVX is the current one. Okay, so let's say you have, let's say you have four, you have four arrays, float A, float B, float C, float D. And you want to do a multiplication and add operation of arrays A and B and C and store the answer into D. If I ask you to do this using C, you will probably do this using a for loop over here. So this is something we all know by now already. Now the problem is in a scalar operation, this will go on. This is a scalar operation. Although you have a vector over here, but this is a scalar operation. So this will run 8 times. This will run 8 times. It's 8 instructions. It's 8 iterations. Sorry, not 8 instructions. 8 iterations you will run for. Okay. Now, by using the AVX instructions, we call MM256. Okay, add instruction. This is the add and multiply. So the M here stands for multiply, and then add instructions. And then you just before you do the instruction, you move the vectors into the 256-bit registers. By doing this, you can perform this entire array in one go. One go. Technically, you can achieve up to 8 times the speed up. You won't actually get 8 times, but in theory, you can actually get up to 8 times the speed up here. That's pretty amazing. At the instruction level parallelism, which you can do today. You don't need to know assembly language. You just need to know what are the Intel intrinsic functions that you need to call. And this website actually gives you a walkthrough on how to do it. It's a good tutorial. Okay, I would like you all to go through it yourself. Okay, so that they explain to you very well. I'll just go through quickly with you all. A few intrinsics. Okay, so these are, they put here __128, 128-bit vector containing 4 floats, 128-bit vector containing 2 doubles, 128-bit vector containing integers. So one integer is 4 bytes, so you can store 4 integers inside here. 256 bits containing 8 floats, 256 bits containing 4 doubles, and 256 bits containing 8 integers over here. So this is how you can define your data types. Okay, AVX2 will use the 512 register variables. And then they have the function naming over here, MM. Okay, the bit width identifies the vector. Okay, the name, the operation, and then the data type identifies the data type of the function's primary argument. The last part tells you whether it's a float, single precision, D means double precision, packed single precision, PD means double precision, and then the EPI are for vectors which contains what? Signed integers, unsigned integers, okay, and so forth, and so forth. Okay, so an example here, let's say you take this particular instruction name, MM256 SRLV. Okay, even if you don't know what SRLV means, the 256 means that the function returns you a 200. This function returns you a 256-bit vector, and the EPI 64 tells you that the arguments contain 64-bit signed integers. Okay. All right, that's how you do. So to build an AVX application is as simple as this. Okay, so I'm going to compile this code now. Okay, I compile this code. I'm going to go into my Ubuntu. Okay, I think I have this code over here. I pasted here just now already. It's the same code. So what I'm doing over here, okay, I have to include the header file for Intel intrinsics for GCC, my standard header file. So we're not doing any threads inside here. We're going to leverage on the hardware's AVX architecture to do data parallelism. So here I'm setting a set of values. I'm setting a set of values into a 256-bit AVX variable. I'm setting another set of variables into another 256-bit variable over here. Okay, so you can think of this as array elements. Array elements. So you can have an array, then you can populate the array elements into here, and then all I have to do is I call the AVX function subtraction. Okay, subtraction, packed scalar. Packed scalar means what? Packed scalar means you will compute between the two ones. So if you want, I can do packed scalar operation. So you will do a scalar operation. No, so you'll take packed, you will take each of them, you will subtract them together. Okay, you subtract them together, and then you will print the answers out for you here. The answers will be stored inside here and the 256 bit variable, and then you can use a pointer to get the address of this register variable, and then you can print out the values inside. That is how you can use AVX in C. Seriously, it is pretty amazing. No, you can not only now if you think data parallelism, you can not only leverage on multi-core architecture, you can then further expand the data parallelism of single core, because each core supports AVX. And then each core, you can call the AVX instructions. Each thread, you can do AVX programming. So you can further improve the parallelism of your multi-core architecture. That is the kind of advantage you can get with AVX over here. Okay, so if I have to clear this up. Okay, to compile this, what do I do? Very easy. Call GCC. All right, call GCC. And then after that, I need to call this command, -mavx. You have to call this command, -mavx, -wall, and then _1, and then output, then a compiler code. Now, how do you know by default your AVX is enabled? How do you know by default? So this is something I didn't cover in the lecture. No, this as I said, this is not examinable, so I'm just putting this in as the best effort for you all to learn. Okay. You can call this function GCC Q to get information about all of the features which are either enabled or disabled in your compiler. So here it shows that AVX is currently disabled. AVX is currently disabled. So if you want to enable AVX, which means that your code is not optimized to use AVX. It's not optimized to use AVX. So if you want, you can use compile this. You can compile this. You will use AVX, and then your code will be optimized. But at the same time, you can do this. Yeah. Sorry. Yeah. You can do this. You can call GCC-Q help target, specify native, which one? AVX. So you want to specify AVX to be native. This will enable your AVX and AVX2. So now when you compile a code with AVX, and then when you run the code, this is what happens. You get all the answers over here. 1, 1, 1, 1, 1. What is 1, 1, 1? Because why? You subtracted each value over here. So let's say I change this value. I put this to 18. So 18 subtract by 15, the answer is 3. So what is happening here? What is happening here, guys and girls, is this. Okay. What is happening here is that the even, so the underscore MM256 register for events. This is a AVX register. This is the AVX register. Will store how many? 8 floating point values. 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then the second one here will store another 8 floating point registers. 1, 2, 3, 4, 5, 6, 7, 8. So this is MM underscore 256 odd. All right. So inside here, you populate the values 2.0, 4.0, 6.0, 8.0, 10.0, 12.0, 14.0, and 18.0. So this can be array elements. You can put your array code inside here and then the array iteration, the array index. Okay. And same thing here, you can also do this is 1.0, 3.0, 5.0, 7.0, 9.0, 11.0, 13.0, and 15.0 over here. This shouldn't be 18. Okay. Now, after this, when I call underscore mm256 underscore sub packed scalar, and I pass in the evens and odd, and I store the answer into where? Into a result. So what happens is this. Maybe I shouldn't have done this. Maybe I should have. Okay, so when I call the operation sum here, when I call a sum here, it takes this value and this value, subtract them together, and then it will store the answer into here. It will take this value and this value, subtract them the answer, and then put the answer into here. So which means in this case, 2 minus 1 is 1, 4 minus 3 is 1, all the way in until the last one, where you will take 18 minus 15, the answer is 3.0. And this is by calling the mm256 underscore sub underscore ps, and this answer is stored inside mm256 result. And then by taking a pointer to the address of this result, you can then print out the values over here. If I were to print out the values over here now, you can see that I have my answer 3 coming out here. Hey, we're thinking, why isn't the 3 not at the last element? You all notice or not? Shouldn't the 3 appear as the last answer? Why is the 3 appearing as the first answer here? Who can tell me? Anyone want to give me a guess? Why is the 3? You see, 2 minus 1. Guys, look at the screen. Guys and girls. 2 minus 1. 2 minus 1 is supposed to give me 1. 4 minus 3 is 1. 6 minus 3 is 1. 8 minus 7 is 1. 18 minus 15 is 3. But when I print out the answers, I print out f of 0. F of 0 is supposed to contain the answer for 1 over here. But instead, f of 0 is showing the answer of 3. Why is that so? Who can tell me? Anybody? It's inverted. Yes, it's inverted. Good, Nasser. It's inverted. Why is it inverted? Why is it inverted? Because the registers are stored in little endian format. Little endian format. So when you populate the values into the register, it's stored in little endian format, which means the lowest address in memory will store the least significant value. The lowest address, little endian means what? The lowest address in memory stores the least significant value, the lowest address in memory. So that's why when you return back the address, and when you try reading the address at the first address in memory from result here, f of 0, it's actually giving you the answer of 3. So how you actually put the data into the register also matters. So this is something that is discussed inside this particular online tutorial over here. How you load the memory, how you do it, everything is mentioned inside here. The arithmetic instructions, these are all you can do, the add, sub, and everything. All right, so it's a very good exercise for you all to do. Okay, I will leave it for you all to go through this. I mean, if you have a time, I know you're all busy with assignments and other units also. And let me emphasize again, the content of this article is not going to appear in this online article is not going to appear in the exam. The content of the lecture today will appear in the exam. Okay, where I already emphasized earlier on, so please refer to the lecture video. Okay, but the content of this online website is not going to appear in the video, but it's a very good hands-on for you all. Because I really hope you all will take this into consideration next time when you do parallel computing in the future, whether you're doing it in the industry or you're doing it for any additional research work or activities. Okay, so that's about it for this week's lecture. Before I conclude the lecture, any questions, guys and girls? Before I stop recording, any questions? Any questions? Any questions before I stop recording? Guys and girls? No. Okay. Okay. So in that case, I think that's about it for today's lecture. I hope everyone is doing okay with the assignment. I think I've been receiving a few questions from Slack. I've not replied back to the questions yet. I do apologize for that. That's because I've been and also through email also. That's because I've been using the whole weekend to finalize the exam questions and also to work with my Australian counterpart to review the exam questions. So we had to get that done by today, Monday. So that's why it was a bit of a rush over the weekend. But in the coming days, I will focus back on the assignment. I'll try to guide you all and help you all out on. If you have any issues with the requirements of the assignment. All right. Okay, so that's about it for today's lecture. So thank you very much. Thank you. I will. Okay. Yes. No worries. I'm glad you all like today's lecture. So it's a very useful lecture. I hope you all will find Cindy very interesting for you all in the future to come. All right. Thank you very much, and I'll see you all tomorrow in the tutorials. Okay. Okay. Thank you. Thank you very much. See you all.